the video, Sabri?
Yes, you can launch. Yes, we launched the video and then
okay.
I disappeared.
It's time.
Thank you.
I'd say the space industry is quite active and quite special.
There is no job where you don't have multidisciplinarity. You have to be curious and to not just do what people ask you to do.
Every day I start working on communicating a new project. It's a completely different work for me.
Every field you can imagine, you can find a way to have an impact in space exploration. The number one difficulty is to find what you really like and what you really enjoy. If you found what you like, then the most difficult step is already done.
So really, go for it. There's something in space that I think unites people. There's lots of countries involved there and they all work together amazingly well. I think it's way more important than we realize. I'm hoping for a bit more women in the space industry because we are not that many, and sometimes when you see panels it's all male and you think, okay, aren't there any great women? And yes, they are. So I'm hoping for a more diverse space community.
And to go further to the moon, to Mars, and so on.
We really produce something which people want. The data our satellites deliver to our end users is something which makes a difference even to everybody's daily life, because every weather prediction you see on your smartphone, on the TV screen, does rely on the data we deliver. And being part of that process, of that organization, is great. My job is to make sure that the original user requirements of the National Weather Services are finally being met by the satellites being flown in space. A user requirement could be, for example, a high-resolution wind speed. And requirements engineering makes sure that the final satellite, the instrument, the ground processing all work together such that the wind speeds which are produced meet the requirements of our users. I think Darmstadt, and especially the area, offers a lot for work-life balance. You can go, in 20 minutes you are in the middle of the Odenwald, in the forest. You can go hiking, you don't see anybody. I personally do a lot of mountain biking there, and I can even cycle to work. And on the other hand, if you want to see city lights, you drive 20 minutes and you're in Frankfurt. And if you want to go even further, you're at the airport and you can basically fly everywhere from there.
I work at UMETSAT as a remote sensing scientist, and my focus is on sea surface temperatures and sea ice surface temperatures from satellites. So I've always been interested in science and the environment, but I wanted to do something that meant something and that actually helped people. So working at UMETSAT gave me the opportunity to combine all of these different interests. I think the job I do here makes a difference in the world, as well as affecting weather forecasts. It's also important to understand a changing climate. So we need to know the best possible knowledge of our ocean and the ocean's health so that we can monitor it and then understand how this may change in the future.
So the most exciting and rewarding part of my job is obviously when we have a launch and we get the first telemetry into the ground segment we just built, and we have the first payload telemetry coming in and the first products coming out. This doesn't happen every year, but we are working several years towards such a target. I believe the job I do makes a difference, especially when you watch weather forecasts on the TV in the evening, which is made with images or data we provide from EUMETSAT. And also, for example, in the recent hurricane events in Florida, we provided support to NOAA to do their own forecast and see where the hurricane would go. So I really think it makes a difference.
Since the 1980s, OIP's sensor systems has been an electro-optical partner for ESA. OIP developed custom-made high-performing optical payloads to provide images of planets in renowned missions, such as Probe 1, Mars, and Venus Express. Our compact visual monitoring cameras are used to monitor the effective performance of and to make scientific images to be studied down on Earth. OIP's spectrometers support ESA and other space partners in planet observation missions, such as Probe 5. Those spectrometers are also used by scientists to analyze the Earth, Mars, and Venus atmosphere on board of Altius, Nomad, and SWAR. If you are looking for high-performance visualization from Earth to space, OIP is your partner by excellence.
Space is part of our lives today, bringing many benefits. In the near future, space will become an even more important part of our lives. Bringing these benefits to us requires numerous technologies to work together. Space Application Services has been developing and delivering technology-enabled services, bringing the benefits of space to Earth for more than 30 years. We plan, prepare, develop, and operate equipment in space for our customers, such as the European Space Agency and NASA. Our strategy is to identify the right question, do the research, and develop the most suitable business solution. Today, we already provide anyone regular and frequent access to space. We open the door to research and manufacturing of novel products that do not exist on Earth. We train the astronauts of tomorrow, and we keep those working in space healthy and safe. We provide technology for in-orbit construction of low Earth orbit space stations and platforms. These will be the industrial powerhouses driving tomorrow's emerging markets, providing advanced materials and medicines. In the next decade, not only will we harvest the resources that are plentiful in space and which are depleted or scarce on Earth, but human settlements in space will use these resources to sustain their independent lives. Our technologies are improving life on Earth by predicting space weather events that can damage our electricity grids. Our astronaut exercise devices help to rehabilitate injured persons, and our robotics replace humans in hazardous environments. This is the near future. Space Application Services will be a part of it. We'll be happy to work on this future with you.
Travailler au pôle spatial Rue du Transine, c'est faire partie d'un espace de travail stimulant offrant de nombreuses opportunités professionnelles. Milieu à haute plus-value, le pôle accueille des entreprises internationales dédiées aux applications spatiales. D'un côté, le centre ESSEC de l'Agence spatiale européenne à Redu. De l'autre, le parc d'activités économiques de Galaxia, développé par Idelux à Transine, qui comporte un centre d'entreprise, un incubateur de start-up, l'ESSEC Galaxia, l'Eurospace Center, le Galileo Integrated Logistics Support Center de la Commission européenne ou encore Vitrociset. Ingénieurs, équipes pluridisciplinaires, start-ups et étudiants, des hommes et des femmes venus du monde entier s'y côtoient chaque jour au sein d'infrastructures modernes et innovantes, d'où naissent des projets de grande envergure, comme la gestion de l'opérationnalité des stations du système Galileo. Travailler au pôle spatial Rue du Transine, c'est faire partie d'un espace de mobilité situé au cœur de l'Europe. Entouré de grands axes routiers et le long de l'autoroute E411, le pôle bénéficie d'accès fluides et rapides depuis Namur, Bruxelles, Luxembourg et tous ses environs, en voiture et via les transports en commun. Travailler au pôle spatial Rue du Transine, c'est faire partie d'un espace authentique et naturel. Lieu de gastronomie et de patrimoine, la région entourant le pôle offre des occasions de sorties variées, telles que le festival de Chasse-Pierre, la foire agricole de Libramont, Libin et son musée Mudia, ou encore le village du livre de Redu, ses infrastructures sportives modernes, son cadre naturel propice aux balades et ses nombreux lieux touristiques comme Bouillon, Bastogne, Durbuy ou encore La Roche en Ardennes. Travailler au pôle spatial Rue du Transine, c'est faire partie d'un espace culturel porté par de nombreux centres urbains rapidement accessibles. Namur, Luxembourg, Liège, mais aussi Marches, Rochefort ou Libramont. Situé à seulement 40 minutes du pôle, Namur propose une vie citadine dynamique et de multiples activités culturelles, musées, théâtres, expositions ou encore concerts. Travailler au pôle spatial Rue du Transine, c'est faire partie d'un espace de vie de qualité pour développer un réseau de connaissances et fonder une famille. Logement à prix accessible, proximité de centres hospitaliers ou encore universités, haute école et écoles internationales sont autant d'atouts essentiels pour le bien-être des habitants de la région. Vous aussi, faites partie du pôle spatial Rue du Transine. Rendez-vous dès maintenant sur invest-in-luxembourg.be.
My name is Nicolas Hartmann. I've been working for 3 months here at Vitrociset Belgium in Transine as a ground system engineer.
My name is Lise Mouton and I am a recruiter and employer branding at Vitrociset Belgium.
My background is engineering for 5 years, and the purpose of my job is to be sure that there are not any issues with the infrastructure on the Earth for the signal coming from the space.
Well, my background is a bachelor degree in human resources management, and I joined Vitrociset Belgium 2 years ago, firstly with an internship of 1 year and now for the undefined contract.
I chose Vitrociset because I really wanted to work in the field of space, and after my master thesis they asked me if I wanted to join the team, and I said yes directly.
First of all, I was afraid because I didn't know nothing from the space domain, but all the colleagues explained me their job, the duties.
I loved space for a long time now, so I wanted to work in not only for passion but to work. Every day is different because you don't know what really you have to do. Sometimes you have to plan to go on travel somewhere. Sometimes you have to work on a project.
I chose to join the company because they were open to have a junior profile.
What I really like here, it's a family-sized company, so it's not too big. So it's really easy to talk with people if you have an issue or something.
Everyone knows everybody. We are around the same age, and there is a good atmosphere, good ambience.
They have strong knowledge in the Galileo program, so for a young engineer as me, it's really interesting.
It's exciting to work for a space company. Everyone can have an access to join the space domain, so why not you?
Space and its exploration has fascinated humans since centuries. We send a few space probes in the solar system. We have even sent robots and rovers on Mars surface to explore it. And we even had a few city trips on the moon. We also have people living in space in the International Space Agency every day since a couple of years now. But the next step, the step further to learn more about space, is definitely to go on Mars and to have manned exploration of Mars. How easy is it? Can we just take our lunch packet with us and go on Mars? No, definitely we cannot do that. Because we need for our life oxygen, water and food. And those elements represent massive amount of weight that we cannot just stand on Mars. So we need to recycle waste to be able to sustain their life during space exploration, long-term space exploration. And this was the idea that was developed in the MELISA project by the European Space Agency 25 years ago now. In the MELISA project, the scientists are trying to build an artificial ecosystem that will allow recycling all true waste, urine, CO2, but also fecal materials if needed, to produce oxygen, water and food to sustain life of crew during years of mission. In the University of Mons, we are working on oxygen production based on cyanobacteria using different nitrogen sources. The University of Mons also participate to this space exploration and try to develop new methods to follow and optimize oxygen production by those microorganisms. Those projects also have a lot of application on Earth, because treating nitrogen waste, urine for example, using cyanobacteria is also a major challenge for space but also for Earth application. If you want to learn more about this, just follow my talk about the MELISA project and the human's implication in producing oxygen in space using cyanobacteria. See you.
Of the video. So, hi everybody. I will make some short interviews before starting Switch to Space, and I come to you, Maerten, to ask you what is your path and how did you come to space?
How do I come to space? Yeah. So my name is Maerten Baes. I'm professor of astronomy at Ghent University. And I study galaxies and the evolution of galaxies. And so if we want to do that, this is best done at all wavelengths, also those not accessible from the Earth's surface. So we use space satellites to study galaxies and galaxies evolution. And it's...
But you, how did you come to space?
How? Well, I studied mathematics and then I got interested in astronomy, and then all of a sudden I started doing a PhD, and then I started.
But you start with mathematics.
Yes, absolutely.
You don't know that you would go to space.
No, at that time, no.
And what's happened? How it's happened?
I don't know. I got a bit tired of the mathematics, and I wanted to do something more tangible, something more, not that space is so tangible, but something more applicable. And so I found physics and astrophysics kind of a very nice application of mathematics and science, and I went into that direction.
Okay, thank you. It's just to give ideas to the students. And so a career is not something linear. And you, Vincianne, just going to my video.
I came to space, yeah, that's a long path. I wanted to study volcano. So and now I'm studying volcanism in the solar system. So at the end, it's not too bad. But yeah, that was...
What's happened? How did you come to space?
Opportunities, I guess. So I contacted someone in Houston saying, oh, I would like to work with you. And that professor said, okay, but you know, I do Mars and Moon. And I was like, okay. And that's how I started. So I had the chance to go in Houston at the NASA Space Center. And that's how I started studying the solar system.
Okay, thanks a lot. I will go to you, Katrien. Yes. Don't present you, so I will present you. But how did you come to space?
I've always been fascinated by the night sky. So I think that's how... early 10s, yeah, very young. So it was clear that I wanted to understand more about that. And then, yeah, I went into studying physics, and the path towards astrophysics was quite clear that I wanted to do something with understanding the universe.
Okay, yeah. The path of Carl-Henrik is more special, huh? But I will present you. But how did you come to space?
So as I mentioned in a previous session, it started when I decided to buy a telescope and starting doing.
And why to buy a telescope?
I don't know. I wanted to do a new thing, and so when I started looking at different objects from the Messier catalogue. With my telescope, I was really amazed by those galaxies, and I had the chance to observe the explosion of a star. So in M82, if I remember correctly, and it was really amazing to see that with the naked eyes.
Okay. Okay, thank you. I'll go to the students. I see the Okay, and you? What are you doing? What are you studying?
I'm studying physics at UCLouvain. I'm in first years of masters.
And attracted by space?
Yeah. Many years ago. Yeah.
Okay, thanks. And you?
Yes, pretty much the same as my colleagues. So I study physics in UCLouvain, and I was attracted to space since I was a child. So I just want to do something with space.
Okay, fine. Okay. Something else?
No.
Okay, thank you. And you?
Hello, my name is Elisa. I'm an aerospace engineer, and I'm currently working at the European Space Agency. In Germany, but I'm in Belgium for now. And yeah.
You have an intern now?
Yeah, I'm doing a traineeship.
Yeah. And why did you come to space? What's happened? How it's come?
Oh, well, I was studying aeronautics, and then I wanted to go...
Why did you study aeronautics?
Well, I wanted to be an engineer, and then aeronautics was the category that just, interested me the most. And then it was not enough. So I wanted to learn a little bit more about, the universe and how everything works. And so, yeah.
So, and you would like to work later in ESA, of course?
Yeah, of course.
Okay, thanks. And you?
Hi, my name is Sirian. I study computer science. I got interested in space because it's a field where it's the bleeding edge of science and technology of many different fields come together. And it's exciting, but it also helps people on Earth. So that's fine.
Okay, thanks. And you?
So I'm actually not in the space area. I'm a bioscience engineer in synthetic biology, but I'm just very interested in space and especially also life in space. So
and maybe
maybe in the future I would, but we'll see.
Thank you. And you?
Hi, I'm Jerome. I do a PhD in geochemistry. I work on meteorites and isotope in meteorites.
Yeah.
I started because I had the opportunity, of course, and because I was always interested in how things work, and so studying the building blocks of the solar system was always interesting for me.
Okay, fine. And you?
I'm also a bioscience engineer, as my colleague here and my colleague here, and so in synthetic biology. And I'm just I'm just interested in all kinds of space science. So, and maybe there are some opportunities for synthetic biology in space as well. So.
Okay, fine. And what did you expect from Switch to Space?
Exactly this, I think, just getting to know what the research is all about here in Belgium and in Europe. So.
Okay, fine. And you? Hi.
Hi. I'm a researcher at KULeuven. I'm doing climate policy research. But I'm a space enthusiast, so I'm here to learn more about it.
Interesting, because you are someone who are not studying space, but you are coming to space by another link, by what? By your study?
No, actually, I have always been interested in knowing more about the space, you know, through TV shows, movies, and stuff. So that's why I'm here.
Okay, thanks. So we have some more minutes. So you are just arrived. I would like.
Hello.
Yeah.
So I'm Ulrich. I'm from the Master of Space Studies at KUL, which is an advanced master's, following up my degree of engineering.
Okay, fine. And what do you expect from Switch to Space?
Yeah, to get information about space and the sector and how the industry works, and the science as well.
Okay. Some of you were at Switch to Space 1? No? Only one? You hear about Switch to Space 1 2 years ago? No? Okay, but I will explain what is Switch. So we will start. Good evening, wherever you are, be it in Belgium and or somewhere else in the world. And some are joining us from very, very far countries. And every day I check to see some countries. And today there are people from Abu Dhabi, from Palestine, from Thailand, from New Zealand, and of course from many European countries. So we are today around 264. We have 264 registration for this topic, and I think this is great because it means that space links us beyond the borders. So Switch to Space, it's an event made for you, students and young professionals. It's dedicated to you, and I will explain why. Well, we have been into numerous universities with space experts, of course, and we observed that you love to see launches of new rockets, new spacecrafts. You love to see movies or pictures from space. You love to see astronauts working on a rocket, but you don't think to embark on a career in the space sector. This is really strange, and it's unfortunate because the sector is in good shape and continues to actively recruit. So there is a problem. Where is the problem? And personally, I have two explanations. The first one, the sector is too discreet and lives too much into its inner cycle. The second one, the career perspective in space, within space, greatly expand today to numerous fields.
biology, medicine, agronomy, economy, defense, security, law, application. And the diversity of its scope is not yet well known, and it's still difficult for students and young professionals to find an overview of the numerous possibilities of jobs in space. Reason why the super Switch team, it's a Belgian Switch team, decided to launch the second edition of Switch to Space. Switch to Space, it's an event organized on 8 days with more than 40 speakers. And today is the day 5. It's the day 5. Yeah, it's the day 5, and the topic, you know it, it's about exploring universe. So the speaker will share with you the expertise, of course. The expertise will explain various opportunities of career prospect in space. They will share insight into the individual path, their jobs, their vision of the future of space, just to help you to find the best way for your future career. Yes, Switch to Space, definitely, it's the key that opens the path of the possible. Make your professional life exciting and enjoy Switch to Space. Thank you. I will now pass to present our Switch leaders of the topic. And we have Katrien, Carl-Henrik, and we have Véronique Dehant is with us. She's remotely because she cannot come here. So Katrien, yeah. Hello, hello Véronique. I begin with Katrien.
Hello.
Katrien Kolenberg is professor of astrophysics at the University of Antwerp and the VUB, Vlaamse Universiteit van Brussel, as well as team coordinator and currently Flemish SRO coordinator at KULeuven. Her research lies in the field of stellar astrophysics, particularly variable stars and asteroseismology. Katrien is passionate about scientific research, astronomy for development, and innovative artistic science communication and education worldwide. She has received international awards from both scientific accomplishments and science communication. Carl-Henrik Dahlqvist. Carl-Henrik, it holds many degrees. First, a master's degree in business engineering at UCLouvain, Université Catholique de Louvain. Also a PhD in finance. He was also teacher assistant in finance in Université de Namur. He holds a master of science in particle physics and cosmology, and he started in October 2018 a second PhD following exoplanet imaging at the Star Institute at Liege. And his current interests lie in exoplanet detection, high contrast imaging, optics, solar physics, spaces, and planetary science and satellite conception and operational management. I don't know in what you are not interested in, Carl-Henrik. Véronique Dehant, she is with us remotely. Véronique is head of service at Royal Observatory of Belgium, where she is responsible of the operational directorate, referent system and planetary science. She's also extraordinary professor at the Université Catholique de Louvain. She's academician since 2010 and was awarded with several prizes, including the Descartes Prize of the European Union in 2003. In 2015, she has obtained an European Research Council Advanced Grant with the project ROTANUT, Rotation and Nutation for a Wobbly Earth. She's principal investigator of the experience LARA, Land of Radio Science, selected for the ExoMars 2020 mission, and the mission was postponed, I think,
postponed to 2022. I give the floor now to Katrien. She is with Carl-Henrik, the leader of the topic.
Very much. I briefly take off my mask and switch on my mic. So today the topic is exploring the universe. Because space missions, they allow us to explore the universe, but the universe is vast and there is a lot you can explore. And today, so our team has selected speakers, actually the world experts that are on Belgian soil in different topics that provide you a tour of our universe. So we can start closer to home. I mean, when you explore the universe, you typically start closer to home. You can, for example, look at our sun, at solar weather, how this influences our planet. And for that, we have joining us today remotely Giovanni Lapenta, so I'll introduce him later. You can also look at habitability in our solar system, Mars, or one of the icy moons of the giant planets. So there's a lot of questions about life here, also how our solar system formed and how it evolved. And actually meteorites play an important role in this. And so we have expert Vincianne Debaille here with us today to talk about that. I'll introduce her later. So this question about life in the universe, life beyond Earth, is one that has triggered us since a long time. And since actually 25 years, we have found planets circling other stars, so-called exoplanets. And today we have also remotely with us a world expert on exoplanets, actually the discoverer of the TRAPPIST exoplanet system, Michael Gillon, who will join us from Liege. And then, as I said, this universe is vast. The stars that we have now found exoplanets around, they're still within our own Milky Way, but you have hundreds of billions of other galaxies, and all of these form a giant web. So there's a lot of mystery around cosmology. And today, Maerten Baes from the University of Ghent will talk more about that to us. So I'll now introduce the first speaker. We will start with the exoplanets and the search for life beyond our solar system. And we are very honored to have with us Michael Gillon, Professor Michael Gillon from the University of Liege. And I'll briefly talk about his interesting parcours. So he is an FNRS Senior Research Associate at the University of Liege. And after his studies in biochemistry and in astrophysics, so he got a master in biochemistry, a PhD in astrophysics at Liege between 1998 and 2006. And then he embarked in a scientific career in the field of exoplanets. And to this field, he has brought many significant results. Notably, as I mentioned, he has led the detection of the fascinating TRAPPIST-1 system composed of 7 Earth-sized planets, some of them even potentially habitable, in orbit of a nearby tiny star. So, Michael, thank you for being with us. The floor is yours.
Hello, everyone. Good afternoon. Thank you for this nice introduction, Katrien. So let me share my screen. So do you see my slides?
Yes, perfectly.
Okay. So it's my pleasure to be here remotely, unfortunately, with you today to talk to you about exoplanets and how this fascinating topic is putting us closer, bringing us closer and closer to an answer. There's life elsewhere in the universe. So since I'm a kid, I'm fascinated by the question: is there someone or something elsewhere in the universe, and how unique is our world? And this question has been raised for centuries, and most people are fascinated by this question. And now we're getting closer and closer to an answer. But before talking about how to answer this question, we have to look at our planet, at our world. and to see how peculiar it is compared to the other planets of our solar system. And our planet is a rocky planet, so it has a solid surface. It's mostly composed of rock and iron. But what makes it really peculiar is the presence of liquid water on the surface of the planet. Such a planet is called habitable planet because all forms of life on Earth depend on liquid water. You have here an image of some cells. They are mostly composed of water. And so by extension, in our quest for life elsewhere in the universe, what we want to detect is first a planet that looks like Earth, which is habitable and which has liquid water on its surface. So you can see here by the size of this small droplet of water here that water content of Earth is really, really small compared to the bulk composition of our planet. It's only 0.02%, but this is what makes the difference between our world and a sterile world like, for instance, Venus. So to have a planet that has water and liquid phase on its surface, you have many features that are important, but the one which is really critical is the distance to the star. Here in Lagrange, it is the sun. So if you are too close to the star, of course, water will evaporate. If you are too far, it will freeze. So with the right atmospheric composition, you need to be in the right range of distance, what is called the circumstellar habitable zone of the star. And if we look at our solar system, if we make some computations, take into account the greenhouse effect and the light coming from the sun, we end up with this green area here, green ring, which is the habitable zone of the sun. And we can see that if we look at the 4 terrestrial planets of our solar system, Mercury is far too close. Earth, of course, is within the habitable zone. Venus is a bit too close at the edge, at the inner edge, and Mars is at the outer edge of the habitable zone. And thanks to space exploration and astronomy, we now know that Venus and Mars are not at all habitable. They are not at all like our world. So Venus has a very dense atmosphere, very rich in CO2. It has undergone what is called a runaway greenhouse. It has been basically too heated, and it has hellish temperature on its surface of several hundreds of degrees Celsius. And oppositely, Mars, the tiny Mars, has lost most of its atmosphere, and it doesn't have the right atmospheric conditions to have liquid water on its surface, and furthermore, water is gone from the surface of the planet. So there's maybe some liquid water beneath the surface, but clearly the surface of the planet is not habitable, so it's not an Earth-like world. And if we want to find an Earth-like world, we have to look much further away than our solar system. We have to look at the stars. And fortunately, in our, let's say, cosmic neighborhood, there are plenty of stars. So our sun is part of a big cluster of stars, which is called the Milky Way. It is a galaxy which contain something like 300 billion stars. It's a big, very big disk composed of stars. And this, you can see it in the sky like a band because we are embedded in this big disk, in this big structure. And until very recently, we didn't know if other stars had planets. And then in 1995 came the first historical discovery of a planet around another star. And it was done by these two Swiss astronomers, Didier Queloz and Michel Mayor. And they received for this a Nobel Prize in physics in last year for this historical discovery that really initiated a whole new field of research in astronomy and science. And this field has developed dramatically and is still developing dramatically now with many results, many projects coming. Every day you have new results in this field. And this is illustrated here with this histogram that shows a number of exoplanet detection as a function of the year, starting with 1995. And you see this quasi exponential increase of number of detection. And now we have more than 4,000 exoplanets that have been discovered so far. And thanks to this, to the large size of this harvest, we can draw some very meaningful statistical conclusion. And the most important one is certainly the fact that most stars in the galaxy, and by extension in the universe, must have its own cortege of planets, its own planetary system. Planets are the natural byproducts of the formation of stars. They are not at all special things, very rare things. Secondly, planetary systems are extremely diverse, much more diverse than we previously expected, based only on our solar system. We have systems that are super compact with plenty of planets of a few Earth masses that are very close to the star, like this KULeuven system. You have giant planets that are super close to the star, which is called hot Jupiters. You have planets around 2 stars or in triple system. You have planets with very elliptical orbits, and not like our planet in the solar system, which are mostly circular. You have free-floating planets that are traveling between stars. You even have planets around dead stars, like neutron stars, pulsars, and so on. So there is a real zoo of exoplanets. And among these thousands of non-exoplanets, there are a few dozens of them that are small and low mass enough to be probably rocky planets, and that are orbiting the habitable zone of their stars. So we don't know yet if they are really habitable, but they are said to be potentially habitable. And these planets are, of course, very interesting in our quest for life elsewhere in the universe. And so what we would like to do now is to study these planets in detail and search for traces of life. And one way to do it, and the most, let's say, elegant way to do it, would be to take a very, very big telescope and to make images with a super high contrast and high resolution that show the star and that show the planets close to it, and then study the light coming from the planets. Such direct detection of exoplanets has been achieved for a few dozen of exoplanets. So you have here real images. So most of the images that I show here are artistic view, but here you have real images showing here the first exoplanet directly detected around a nearby star. And here you have a fascinating system of 3 planets imaged around a nearby star. And in Belgium, we have a high expertise in this field of direct imaging. And the next step would be to detect an habitable planet around a nearby star, and then to study its light by spectroscopy. So basically to spread the light from the planet through something like a prism, and spread it in colors, in wavelength, and to study the distribution of the intensity of the light as a function of wavelength, what is called a spectrum. And if you do this on a planet with an atmosphere, what you can get is information about its atmospheric composition. Because at different wavelengths, you will have different absorption of the atmospheric components that will imprint the spectrum. So here, what you have here is the spectrum of the Earth, observed in the infrared from space. And you can see some clear patterns that are due, in fact, to the absorption by the, some molecules of our atmosphere of the light coming from the surface. So you have here a water structure, you have here an ozone structure, you have CO2, and altogether these 3 molecules are a strong indication that something very interesting is happening on our planet, which is photosynthesis, in fact, and so life. So we would like to do the same for exoplanets. And so there are several projects that are in preparations that want to achieve this, to detect an habitable exoplanet around a nearby star and to study directly its light and to search for traces of life. So far, the exoplanets that have been directly imaged are giant planets, very far from their star. We still need technological development to do this for habitable terrestrial planets that are much smaller, much cooler. And so you have here the extremely large telescope, a European telescope that is 40-meter diameter in size. So it's a huge, huge telescope that is being built in Chile that should be operational in 2025, that could achieve some detection of habitable planets. and you have some space mission concepts like ABEX that are in development. But it will take time. Anyway, there's maybe a shortcut to study habitable planet, which is based on a phenomenon called transits. So in astronomy, a transit is something very simple. It's the crossing of something small in front of something big. And here what you have is an image of Venus passing in front of the sun. So it's called a transit of Venus. For exoplanets that are very far away, we are not able to do this kind of nice image. But what we can do is to measure very precisely the brightness of the star and to see how it evolves. And when a planet passes in front of it, you have a drop of brightness that indicates the presence of the planet. This is how most of the planets, exoplanets, have been detected so far. And when you have such a transiting configuration for an exoplanet, you can even study the atmospheric composition of the planet. Because when the planet is in front of the star, a fraction of the light emitted by the star in our direction will pass through the atmospheric limb of the planet and will be filtrated by the atmosphere. So there will be some absorption, some scattering by the components of the atmosphere of the planet that will imprint the spectrum of the star. By comparing the spectrum of the star outside transit and within transit, we can learn about the atmospheric composition of the planet without even seeing the planet. It has been done for many giant exoplanets, and now we would like to do it for smaller terrestrial planets and search for possibly traces of life. But the problem here is that for an Earth-like planet, there is a huge difference in size compared to the star. So you have here Venus that has the same size as the Earth in front of the sun. You can see how small is Venus compared to the Earth and to the sun, sorry. And what we want to detect is a small signal of the light passing within the tiny, tiny atmospheric ring of the planet. So it's really a super, super small signal, and with current technology, we couldn't detect it. So there is this shortcut, which is easy to comprehend, which is to go for smaller stars. If you put an Earth-like planet in front of a smaller star, then the signal from its atmosphere becomes much, much larger. And fortunately, in the universe, most of the stars are much smaller than our sun. They are called red dwarfs, and they dominate the galactic population, the stellar population of our galaxy. And furthermore, because these stars are very small, they emit much less light than our sun. They are cooler also, which means that the habitable zone is much, much closer to them than for the sun. And which means that the planets, they have to be very close to the star to be habitable. So the orbital period has to be very, very small, not 1 year, but a few days, or maybe 10 or 20 days. And so this means that the transits that we are searching for are much, much more frequent. And they even have a higher geometrical probability because the planet is so close to the star. So they are really favorable targets for the transit method. And so there is one space telescope currently in preparation by NASA, ESA, and the Canadian Space Agency that will be launched next year that will have the capacities, instrumental capacities to study the atmosphere of potentially habitable planet in front, transiting nearby very small red dwarfs. And this telescope is called James Webb. It has been delayed a few times, but now it should be ready to be launched next year. But it will depend, of course, of the pandemic, but normally it should be launched next year. And you have here, it will be the largest ever space telescope. And what we wanted to do as exoplanet hunter is to find good targets for James Webb, to find potentially habitable planets that are well suited for detailed characterization with James Webb. So on the US side, there is the TESS mission. It is a space mission that's been launched in 2018 that is searching for this kind of planets. And on our side in Belgium, we're leading a project which has a typical Belgian name, which is called SPECULOOS. It is done in consortium with other institutions from different countries, which is using bigger telescope, but operating from the ground and not from space. And that is scouting the heavens for potentially habitable planet around nearby small stars. And so I show you nice images here of the SPECULOOS telescope. We have 4 of them in Chile. one of them in Tenerife and one of them in Mexico. Of course, it's always in good astronomical sites when you can see where the astronomical conditions are very good, you can have very good observation of the sky. And the project started only last year, but we initiated it before with a prototype using our small telescope, Liege telescope, which is called TRAPPIST, that we installed in Chile in 2010. So it's again a Belgian, typical Belgian name. It's easy to see the reference. And with this prototype, we discovered in 2017 a fascinating system of 7 Earth-sized planets transiting around a nearby small star. And so these planets are illustrated here, just artistic view, unfortunately. And what is really interesting is that these 7 planets are very close to the habitable zone of the star. 3 to 4 of them are within the habitable zone of the star. 2 of them are a bit closer to the star, and 1 of them is further away. And all of them are very well suited for detailed atmospheric study with James Webb. We also have very precise measurement of the radius, of their mass. We now have very strong constraint on their composition. They are definitely rocky planets. We know they are a bit enriched in volatile elements, and we think it could be water, so it makes them very interesting. And from next year and afterwards, we will study them with James Webb. And with SPECULOOS and also with the TESS mission, we want to detect more of this kind of planets. And soon we will have a catalog of planets that will be well suited for detailed atmospheric studies. And further, later, we will see this giant telescopes that will detect planets by direct imaging that will provide also good targets to search for traces of life. So the future in the study of exoplanets and search for life is very, very interesting and very exciting. And I thank you for your attention.
Thank you very much for this very interesting talk, Michael. I think there might be some questions. I will first ask the questions in the public here. I'll take off. I'll take this off. Does anyone have a question? Not yet? Okay, then I think we can take a question from the
Yes.
Yes, thank you.
So I have one very interesting question from Shoruk. And the question is a little bit outside of your team of research, Michael, but it's very interesting. Why are we limiting ourselves by assuming that life on moons and planets other than Earth has the same prerequisites as that on Earth? Isn't it possible that life out there can exist in the absence of water, but presence of another element or other elements?
I can try to answer. So water is a very special element in the sense that it makes possible the presence, the existence of very complex molecules that are required by life. And it gives them also the capacity to change shape, which is also very important, for instance, for enzymes, to have this flexibility. And furthermore, water is liquid, has relatively high temperatures, and the speed, the rate of chemical reactions depend on temperature. If you have a solvent different of water that is liquid at very low temperature, the chemical reaction will be super, super slow. So we think, for instance, that on Titan, there are some liquid ethane and methane. It's very unlikely that life could develop there, but if we are very open-minded and think about possible living creatures there using methane, ethane as solvents, the chemical rates, biochemical rates will be much, much slower. So life will be much slower there, and I don't think it's a big advantage. So it seems logical that to search for life as we know it, to go for liquid water. Of course, we have also to be open-minded, but for exoplanets, for which we are very limited in the information, the amount of information we can learn, I think it's much better to focus on life as we know it, to search for traces of life that we could recognize, and maybe to be more open-minded for in our exploration of the solar system. I don't know if it's an answer comprehensive or not.
Yeah, thank you. I still have some questions, but you want to go, Katrien?
Does anyone? Yeah, I see a question here. So please.
Okay.
How many light years away is the TRAPPIST system from here, Michael?
It's 40 light years.
Okay, so it would take a while to get there anyway.
Yeah.
Oh, with current technology, millions of years.
Okay, any other questions here? Yes, in the back.
Okay. So I read somewhere or heard somewhere that there could be life on Europa, the Jupiter's moon. Are scientists considering that instead of going, outside of the solar system?
Yeah. Did you hear the question, Michael?
Yes, indeed. I'm not sure I'm the best person to answer this, but it's clear that there are some opportunities in a search for life elsewhere in the solar system. But if life exists elsewhere in the solar system, it will be hidden beneath the surface of the body. For instance, on Mars, it has to be beneath the surface. On these icy moons, it has to be beneath the surface under the icy crust, like Enceladus or Europa and so on. And so it requires to be detected an in situ exploration. So we can't just make an atmospheric study from remote using spectroscopy. We would have to send probes and so on. So it's something that can be done in the solar system, but not at all for exoplanets. So and anyway, it will be very different conditions than on Earth. So with exoplanet, we would like to find worlds that look more like Earth. But it's also very interesting to search for life in these moons and on Mars and so on, of course.
Okay, thank you very much. Maybe we can switch back now to the online questions, and then afterwards you might have some more. Thank you.
Yes, I have 2 questions from Jonas. Does the smaller system size and closer orbits of the TRAPPIST-1 planets lead to less orbital stability? Also, if the planets are closer to their red dwarf stars, does that make them more susceptible to solar events?
There are 2 excellent questions, and indeed it was a main concern when we found the system, this dynamical stability. And in fact, the system is very peculiar because to be stable while being so compact requires that the planets have the mutual interactions that are averaging out. And to have this possible, it requires that the planets are in so-called mean motion resonances, which means that basically the orbital periods of the planet are related by integer ratios. And with this peculiar orbital configuration, when there is a strong pull, let's say, of one planet on the other, it will be average, it will be nulled by a push from another planet. This is the same then for the moon, the Galilean moons of Jupiter, Io, Europa, and Ganymede. They have the same mean motion resonance configuration, and this makes the system super stable. We know the system is billions of years old, and it's super stable thanks to this special configuration. Now, for the solar events, for this stellar winds from the star, it's indeed a huge concern that we have, because as the planets are so close to the star, these high energy particles, high velocity particles, mostly electrons, protons that are emitted by the star, must constantly erode the atmosphere. It depends on the magnetosphere, or the presence of a magnetosphere, and the strength of the magnetosphere of the planet that we don't know at all of. But it must play a role indeed in the survival of the atmosphere. And so we don't know at all if they have an atmosphere, their secondary atmosphere survive these harsh conditions or not. This is why it will be so interesting to study them with James Webb. If we detect an atmosphere, it will tell us a lot about the survivability of secondary atmosphere in so harsh conditions.
Thanks. I still have a question, but we can keep it for the end.
Okay, thank you so much, Véronique and Michael. For now, we will move on, but indeed, at the end, there is time for more questions. So if anyone has any question related to this topic, please let us know. And for those who are here, we will take them after the end of the 4 talks and the question sessions. So then now we will move on to the next topic. Thank you very much, Michael. And we have with us here today Professor Vincianne Debaille. She is based at ULB, and she's a geologist by training, and more particularly, she's a geochemist specialized in the chemical composition of rocks to date them and to understand how they formed. And she's particularly interested in the study of meteorites of different origins coming from asteroids, but also meteorites from the Moon and Mars. And with this interest, she has participated in several meteorite collection missions, among others in Antarctica. So we are very curious to hear from you, Vincianne. The floor is yours. Thank you.
It's better like that. Good afternoon, everybody. Thank you for being here. I know the situation is very complicated, and it's very nice to see we have a share between people here in the room and people on the web. So basically here I'm going to talk about meteorite and space. So what I'm doing is, I haven't started, yes. So what I'm doing is to, when you start studying the formation of the solar system, you start with a cloud of gas, then collapsing by its own gravity, then condensing from gas to dust to the first solid of the solar system, and then into planets. And as a geologist, of course, I'm interested in this last step. How do we form planets and how they're going to evolve to have the Earth, for example, as we live on it. And how can you do that? First, you can go for sample directly in situ. It happened, but it's quite rare. And then you can even go further. So we have the Mars 2020 mission that's going to arrive on Mars in February 2021. And we hope to get sample back from Mars on Earth in 2030, so we still have time. But then in the meantime, what do we do? Well, we can wait what nature is giving to us. And here you have several orbits of asteroids, and some of them are actually crossing the orbit of the Earth. So what we do with meteorite, we just wait nature delivering some gift from the solar system. We have a lot actually arriving on Earth every year. So we can divide in micrometeorite, below 2 millimeters in size, dust, and meteorite. You can see that micrometeorite, this is a huge amount. The estimation are giving between 30 to 40,000 tons of micrometeorites, dust, space dust coming on Earth every year. And then we have the meteorite. It's a bit easier because you can really see them. It's big blocks of rocks. And the estimation gives something like 7,000 tons per year. Of course, the 2/3 of the surface of the Earth are covered by water. It means that 2/3 of this amount is actually lost in water. But then sometimes we can recover micrometeorite. It's everywhere, basically. So probably you have micrometeorite in your air. You don't know about it because it's really tiny. You need special microscope. And then meteorite. What do we do? What can we do with those meteorites? For example, we have some from Mars. So for me, it's very interesting. You can study the formation of Mars thanks to Martian meteorite. We have some from the Moon. So of course, we have the Apollo mission. But then the Apollo mission were very restricted in space at the surface of the moon. So you can, for example, sample the far side of the moon thanks to lunar meteorite. We do have meteorite from very specific asteroids. So this one, you can see it's very whitish, it's very strange. It's called a eucrite, and actually we know now it's coming from the asteroid Vesta. Vesta is the second largest asteroid in the asteroid belt, and we do have plenty of meteorite coming from that asteroid. Then we have also iron meteorites. So you know that the core of the Earth is made of iron and nickel, and it's actually impossible to study it. But thanks to those meteorites, we can study the iron formation, iron core of planet and how you form a planet. And then we have very nice one, and you can see it's a mixture of minerals and metal. And this one is still quite mysterious, so we don't really know how they form. We think it's made by impact, so basically you take two different solids that should not be together, and because of impact, you just put them together and then the system freezes. And it's very important because it shows that impact was very, very important in the early solar system. And then we have also the chondrite. So the chondrite, that's the most primitive meteorite we can find. And they've stayed intact since 4.5 billion years. So actually, when we study chondrite, we can study the formation of the solar system with all the dust that appeared very early in the solar system. Of course, I'm very interested in Martian meteorites, and actually we have a lot of them. So we have 280 Martian meteorites today, almost 200 kilograms of Mars actually now on Earth. And the problem is we don't really know where they're coming from at the surface of Mars. So we have seen 4 of them falling, so it's very nice because when you see them falling, you give the name of the place where we found it. We have Chassigny in France, Chergoté in India, Zagami in Nigeria, and Tissinou in Morocco very recently, 2011. And how actually we can have meteorite from Mars. So this is the surface of Mars, and then you have meteorite actually falling at the surface of Mars, and then you have a crater. But sometimes, like at a billiard game, you can have ejection of some sample from the surface of Mars. And it's much easier on Mars because the gravity is much lower compared to Earth. So actually it's quite easy to eject sample from Mars and then have them arriving on Earth. This is a very random process, of course, but we know it's happening. And I cannot resist showing you a very nice crater at the surface of Mars, where you can see actually we had liquid water. You can see all those channels flowing from the crater. So that's very important because cratering is actually bringing, on a very short amount of time, liquid water at the surface of Mars. I was talking about this eucrite coming from Vesta, and we had, so here you have a very ancient image from Hubble telescope, and we had the Dawn mission that was around Vesta in 2011-12. You can see very nice craters at the surface of Vesta, and you can see here it should be a round shape. And actually we had a huge impact at the surface of Vesta that ejected a lot of material, and this material is actually now found on Earth. And for example, 2 years ago we had a new meteorite at the museum that fell in the south of Belgium, and that is coming from Vesta. So where do you find meteorites? Well, when you see them falling, it seems obvious, but actually it's not that easy because sometimes you need to triangulate the trajectory of the meteorite, and it's not because you see one falling in the sky that it's easy to find it at the surface of the Earth. Random find, that's very complicated because meteorites are very often made of iron nickel, and it's going to rust at the surface of the Earth. So a meteorite is not very stable, and especially in Belgium, for example, so it's not very efficient. You can go in hot desert, it's very nice, it's dry, and then they're going to stay a bit more at the surface of the Earth. And unfortunately, hot desert sometimes can be very dangerous. And then you can go in Antarctica, that's the most efficient. And just to show you some numbers, just to prove you how efficient it is, you can see here some numbers of collected meteorites in the collection. I've put some hot desert, Algeria, Libya, Sahara, so we call it Northwest Africa. And you can see that we have more than 10,000 meteorites coming from those places. USA, plenty of desert as well, people looking for it. Belgium 5, well, it's a small country, so of course we have less meteorite, France 90. But then you can see Antarctica, almost 45,000 meteorites coming from Antarctica. Why? First, it's easy to see, it's a black spot on white ice, it's very easy to see. We have also limited terrestrial alteration. We can keep meteorite frozen in ice in Antarctica. They're also protected from commercial abuse, so there is a lot of commercial transaction around meteorite, but Antarctica is protected. It's a continent dedicated to science. And then the most important, we can concentrate meteorite in some area thanks to glacier movement. You know, Antarctica, it's a rock continent with ice on it. And then when you have snow, it's accumulating in ice, and then the ice is forming glacier and it's flowing to the sea. And when a meteorite falls in Antarctica, well, it's just going to be incorporated in the ice and travel with the ice. But because we have mountains in Antarctica, what's going to happen? The ice is going to be blocked by the mountain, and then it has no choice, it has to go up. And then we have strong winds in Antarctica, and the ice is going to be eroded and freeing all the meteorites that have been traveling in ice. And this is what we call the blue ice field, where we know we're going to find meteorites. Of course, Antarctica is not a very nice place. It's beautiful, but it's not very nice, it's very cold. But we know that when we go to those blue ice fields, we're going to find plenty of meteorites. And actually that's going to be a space mission, a very cheap one compared to go in space, but we can collect space rocks in Antarctica. We have several blue ice fields now in Antarctica. So just to let you know, here this is South Africa, here it's Chile, and here it's Australia and New Zealand. And you have all this chain of mountain here. And then we have here some mountains called the Belgica mountain, and we have the Belgica station, the station from Belgium. So here again, we're facing South Africa. You can see here the Sorwanden mountain. And just to let you know, the Yamato mountains, they were the first in 1969 to be exploited for that. So we had Japanese geologists, they went there and suddenly they realized we could find plenty of meteorites. And since 1969, we've had several campaigns led by the Japanese, led by the Americans, and now Belgium as well, to collect meteorites in Antarctica. You may know that we have a Belgian base, and that Belgian base is actually here, very close of the Nansen Blue Ice Field. So thanks to the Belgian base, we can go on the Blue Ice Field. It's very high in altitude, 3,000 meters, but we've been very successful finding meteorites here. You can see, as I said, it's not very nice. The average temperature is between -18, -27. You have a strong wind, which means that the temperature you really feel is actually -36, and that's the summer. So you can see it's not a very good place for vacation, but that's very good for meteorite. And I'm going to finish by showing you a few pictures of this adventure because it's very extraordinary. So as you can see, we do not travel light. We take container to sleep in it. Here you can see the fuel, you can see all the snowmobiles. So it's a very heavy expedition. And then we're sleeping here in this kind of container. We have a wall that we built for trying to protect us against the wind because it's, as I said, it's very windy and you have nothing to stop the wind. And then you can see here a black spot on white ice. As you can see, you cannot miss it. Sometimes you find nothing and then suddenly you see it. It's an Easter egg, but really you cannot miss it. You can see the field here, it's very nice. It's blue ice because it's been compacted. And of course, it's midnight sun because we are below the polar circle. Here again, it's not totally flat. You have some bumps. And again, a new meteorite here. And this one is a huge one. It's 18 kilograms and it's exhibited at the Museum of Royal Science in Brussels right now. A few examples. So this is how we find them on the field. We give them provisionary numbers. And you can see sometimes they're in a very good shape. And sometimes you can recognize them. You can see here this whitish inside. So of course, it's always black on the outside because it's cooked by the entrance in the atmosphere. But you can see here this whitish inside, that's a eucrite. So again, this one is a piece from Vesta, and it's very recognizable because it's very white inside. And I'm going to finish here. So I thank you for your attention. And yes, we're all smiling underneath the mask.
Thank you very much, Vincianne. This is very interesting. So I have a question, if I may. How many kilograms did you bring back?
It really depends. Of course, the problem is the sample are not as big as we would want. So usually it's between something like 50 to 70 kilograms for each mission.
Okay, and then how is it distributed? Because I guess it's an international mission. How do you decide who takes what?
Yeah, so because we collaborate with the Japanese, so we share it between Japan and Belgium, but because it's protected by the Antarctic Treaty, they're all available for free to all scientists requesting pieces from meteorite. Okay. So basically a scientist is just writing a good proposal and then we give them for free sample from Antarctica.
Okay, yeah, thank you very much. Any questions in the audience here? Yes?
If we have meteorites?
Yeah, that's a good question. The problem is that we don't know where they're coming from at the surface of Mars. So that's a very big problem because if you want to date the surface of Mars, you need to know exactly where it's coming from. So that's the first problem we have. The second problem we have is I've shown you that sometimes we can have water circulation. The problem is that when you have water circulating through a rock, that rock is becoming very fragile. And then it's not going to survive the ejection from Mars. Which means that what we see on Earth is very biased. It's only igneous sample, but it's no sedimentary sample where we could find life actually because we had water through it. So it's already very nice. I'm not going to complain, of course, but we're very limited in our understanding of habitability of Mars. If we had life on Mars, because the sample we have on Earth are not helpful to solve that question.
Thank you. Any other questions here? If not, then let's move over to online questions. Véronique.
Yes, I have many questions. The first is from Mathieu. Thank you for your talk. My question is more related to your experience. How did you manage to participate to a scientific mission to Antarctica? At which step of your career did it become an opportunity?
Good question.
Yeah.
Well, science is working in the way that we have to write proposal to get money. And thanks to the Belgian station, we had the opportunity to go there. And when we realized that the Japanese were there in the 80s and we had this blue ice field, for us, it was very obvious. It was a very good opportunity to be able to collect meteorite on the blue ice field. At which stage of my career? That's a very good question. For me, it was just before having a permanent position, but I would say that it really depends on the opportunities. So it's a very difficult question because there is no right answer to that.
Thank you. Then I have two questions which are very similar. Fatma and Jonas. Fatma asked, how do you identify planetary origin meteorites? And Jonas asked, how do you decide which meteor comes from where? Just from similar composition or spectrometry?
Yeah, that's a difficult one as well. So basically, I showed you the three examples where we know where it's coming from. Mars is okay, first the moon. Moon is very obvious because we do have samples from the moon, so we can compare to them. We can compare lunar meteorite to those Apollo samples, so that was very easy to do. For Mars, it was a bit more complicated, and in the 80s, people did not agree on that because it was thought that ejection from a rock from Mars was not possible. And people realized that we have trapped bubble in minerals from Martian meteorites, and they measure the composition of those bubbles. And at the same time, we had the composition of the Martian atmosphere because we had the Viking probe in the 70s. And what happened is that we have a perfect match between the composition of those bubbles and the atmosphere of Mars. So if it's not coming from Mars, it's going to be very difficult to explain the origin of those meteorites because we're a perfect match with the Martian atmosphere. VESTA is a bit more complicated. Again, we needed the Dawn mission, and what we can do is measure at distance the composition of asteroid. And for that, we have a perfect match between VESTA and Euclid, for example. And for the rest, it's more complicated. It's more guess. We try to match the composition of asteroid with what we have in the lab, but it's less obvious than those three examples.
Thank you. And a last question from Siddhar Karha. Do you look for volunteers for your expeditions?
Yeah, I'm very sorry to say you're not the first asking. And we do have a waiting list that is already very long. So yeah, very sorry about that.
I have one question, if we have time.
Yes.
Okay, from Imet. During their travel to Earth, meteorites will face different physical state changes. Is it possible to reverse this change and understand their original properties?
Yeah, unfortunately not. Once you start melting a rock, it's impossible to come back to the original state. Think about a candle. So if you take a candle with a nice cartoon on it, and it's there, and you have the cartoon, but then you start melting the candle. And then when the wax is solidifying, you have back something solid, but then the cartoon has disappeared. And it's impossible to go back to the original cartoon. So unfortunately, those geological processes are really one-way direction.
And that's all from my side.
Okay, thank you very much, Véronique. Is there one more question here? Yes, one in the back there. You can speak loud, maybe we can hear you. Or mic is coming.
Thank you. So we spoke about meteorites from Mars, from the Moon, and the inner belt, but is it possible to get some meteorites from the Kuiper belt or maybe extrasolar meteorite?
Yeah, good question. The problem is when you form the solar system, the further away you go from the sun and the more ice you will have, which means that in the asteroid belt, we have mainly rocky asteroids, but then when you go further and further away, you will have comets. And yes, we can have comets arriving on Earth. The problem is that they're going to melt immediately. So that's not something we can really collect. But yeah, that's the problem. So yes, it's very possible to have a cometary material. It's rarer, of course, but we cannot really collect it. It's going to melt immediately.
Thank you very much, Vincianne. If there are any other questions online or here today, then please keep them in mind and we can have more later on. But now, since we were already in the Kuiper belt, we will move on, leave the solar system and just take a bigger angle because now the next talk is about the cosmological view. The title of the talk is Our Universe, a 13.8 billion years old enigma. And it will be given by an expert in the field, Professor Maerten Baes from Ghent University. So Maerten Baes obtained his PhD in 2001. He subsequently worked in the UK and in Chile, where there's also a lot of telescopes, as you know. And since 2005, he's Professor of Astrophysics at Ghent University. His research interests include interstellar matter, galaxy evolution, and infrared astronomy. He uses supercomputer simulations as well as astronomical observations from ground-based and space observatories for his research. He has co-authored more than 300 publications and has supervised 15 PhD theses and more than 50 master theses. He teaches various astronomy courses at the bachelor and master level at Ghent University and regularly contributes to outreach activities all over the country. And so with this, we're very curious. Maerten, the floor is yours.
Okay, and now. Screen.
Nope, we don't see.
No. Stop share. Share screen. Share. Yes, there we are.
Yes, perfect.
Okay, thank you. Thank you for this introduction, and to disappoint you all, I wouldn't say I'm a big expert in cosmology, but I'll try to do the best I can, and I'll use that as an excuse if I cannot answer your questions later on. But I'm going to talk to you a little bit about the deep universe, and Michael already showed you an image similar to this one. This is our own Milky Way. So all the individual stars you see in the night sky are part of our own Milky Way. And apart from those that you can see individually, there's this milky, smooth white band, which is our own stellar system with several 100 billion stars in it. And that's not the only one, because there's several of them, and we call them island universes. So every galaxy like this is similar to our own Milky Way with several 100 billion stars, and there are billions and billions of those Milky Ways. So the universe is extremely large, and it's nice because these Milky Ways appear in all kinds of different shapes. These are typical, the spiral galaxies that if you ask somebody to draw Milky Way or a galaxy, it will be something with spiral arms. But there's various shapes. You also have these things that are a little bit more boring, but they're interesting in their own right. And so a question that we have if we see this large diversity of galaxies is, where do they come from? How do they form? How do they evolve? And that is what we want to try to find out. And the discovery that these galaxies are really separate Milky Way systems is very recent. It's only about 100 years old. So extragalactic astronomy is a very recent branch of astrophysics. And one of the top developments there came about 100 years ago, and that was by these two people. The one on the top is Edwin Hubble, and you know the name probably of the telescope named after him. But the person on the bottom is a Belgian astronomer, it's Georges Lemaitre, who played an extremely important role in finding out how our universe works. And finding out how the universe works at larger scales is what we call cosmology. And one of these developments is what you see in the top left there, and that is called now the Hubble-Lemaitre law. And these two astronomers found that if you look at galaxies and you can measure in some ways how far they are, and they use different techniques for that, you can also measure how far they move away from us. And they discovered that most galaxies seem to move away from us. And you can find that using the Doppler shift. And that is what you see in the cartoon on the bottom. By listening to a firefighter's truck, you can hear whether it's approaching us or moving away and at which speed. And you can do the same with light. So they found that galaxies move away from us, and the galaxies that are furthest away seem to move away from us furthest. And then Lemaitre was one of the first people to then think, well, this does imply that the universe is not static. The universe evolves. And if things move away from us now and galaxies are all further and further away from each other, they must have been much closer to each other in the past. And that immediately leads to the idea of a Big Bang and a finite age of the universe. So we can essentially try and look at galaxies that are further and further away, and then look back into history, because light always takes time to travel towards us. So we see galaxies, distant galaxies, as they were in earlier days. And so we can try to do that with big telescopes on Earth. This is the Very Large Telescope in Chile, where Europe has this very nice observatory. But if you want to look at galaxies that are really far away, they are tiny on the sky, and you need very high precision, and that is what you best do from space. And this is the current, probably well or most known telescope in space, is the Hubble Space Telescope, that is already operational for more than 25 years now. And if you use the Hubble Space Telescope to look at the deep sky, you see galaxies everywhere. And this is a typical example, one of the most famous pictures that Hubble took. This is the Hubble Deep Field. It's a very small pocket of sky, but it's full of galaxies. And they made an image that's even deeper. This is the Hubble Ultra Deep Field, which is just taking pictures ever for a very long time. You see galaxies everywhere, and most of these galaxies are at very large distances, some of them 10 billion light years away. So by looking at this diverse galaxy population, we can then try to find out how galaxies evolve through cosmic time. Unfortunately, there's new missions coming that will help us with that even more. For example, this is the ESA Euclid mission that is to be launched in 2 years from now. And that will map hundreds of millions of galaxies and look at their shapes and their places in space. And that can help us to see how they are distributed there. And we now already know that galaxies are not randomly distributed, but they form kind of a spider web structure in 3D, what we call the cosmic web. And we want to try to study how this cosmic web evolves through time. And next year, that was also already hinted at, will the James Webb be launched. So this is a telescope that is a successor of Hubble. It's a joint mission of ESA and NASA. And that will be so, will have so sharp images that that we can hope to really image the first galaxies formed at the beginning of the universe. So we look forward to that. But there's even more, because galaxies do not only contain stars, they also contain the material out of which these stars are being made. But that material we cannot easily see in optical light because it doesn't shine at optical light. We have to look at different wavelengths. Problem is that radiation does not penetrate the atmosphere, so we have to do that from space. But nice thing is we can. And for example, we can look in the infrared range, where you can see a very cold material out of which stars are being made. Or we can look in X-rays, where we see very hot material that is, for example, spinning around black holes. And we have missions like that as well. This was the Herschel mission. That was an ESA mission that operated from 2009 to 2013. And that was seeing in the cold infrared radiation. This is XMM Newton. This is an X-ray mission that is still operational, and that can look look at this very hot material. And for example, if you look at this composition of images, on the top left you see Andromeda. That is the big galaxy. This is our neighboring galaxy that we can study very well. And that you see an optical image, how we would look like in real colors if you would see it with our naked eyes. But you can also look at that in the infrared with Herschel and X-rays with XMM Newton. Then you see all kinds of different components of these galaxies. And then you can try to puzzle out how this galaxy formed. And looking, for example, with Herschel at blank pieces of sky in a similar way as the Hubble Deep Field did, looking at a random spot and counting what you see. This is what Herschel did for a bigger piece of sky. And every dot in this image is a single galaxy, many of them at millions and sometimes billions light years away. So looking at all this information, we can try to find out how galaxies form and evolve. And if we put some of that information together, for example, astronomers make plots like this. So what you see here is the total star formation history of the universe. How many stars are being formed every year over the entire universe? And then on the top, you see the look back time, and that you see that the universe now at look back time 0 is not very active. But 10 billion years ago, the universe was way, way, way more active. So way, way more stars were being formed there. And if you go even more back into time, it goes down again. So we want to use the new telescopes to really push this to the limits. And now you can wonder what happens after these 12 million years, 30 million years. We come in a time where actually the first galaxy still had to be formed. And there you come towards the Big Bang. And can we believe this Big Bang or not? Yes, there's plenty of reason to believe that. And this is probably the most convincing proof. This is the cosmic microwave background. So this is an echo of the Big Bang at the very earliest times, where we see little increases and decreases in density that are the seeds out of which galaxies will be formed in later times. And over the years, you see different microwave satellites. Our resolution and our sensitivity is always improving. And so we hope to disclose the secrets of that very early period as well. And so nowadays we have a fairly good understanding of how the universe evolved since the Big Bang over the cosmic microwave background, then the dark ages, and then the period where galaxies formed and evolved. But there's still many questions that we hope to solve in the next few years, and space missions over the entire wavelength range are an enormous help in that quest. So I thank you for your attention.
Thank you very much, Maerten. Yeah, this is a vast topic, and so for me it always raises many questions. I'm curious if there are any questions here in the audience. Not yet, then maybe I can ask one, which is just for your daily life, how old and how far away are the galaxies that you are usually studying?
Personally, with our team, we mainly focus on nearby galaxies. So that's galaxies in our local neighborhood. And then we talk about tens of millions of light years. Why we want to focus on those? Because in those galaxies, we can have the highest detail. So we look at we look at these galaxies in detail, but we also look at very distant galaxies at billions of light years. But then you can mainly do statistics in a way. But we do both, but we focus mainly on the nearby ones.
Thank you very much. Question? Yes.
Euclid. Well, there's various differences, and the most important difference, I think, is that Euclid is a survey telescope, so it has a set goal, meaning it will scan the entire sky with a fixed program, and it has certain instruments for that. While James Webb is a mission that is everyone can ask for their preferred observations, and it has a very high sensitivity and very high resolution. And so it has a different, it's not a surveying for the entire sky, but it's really looking at the details of very individual small fields that you can try to observe. So that will be ideal for both the first galaxies, but also to look at exoplanets or anything you can imagine.
Get some observation time with the James Webb telescope in the future?
Whether I will get some observing time, I hope, but I think many people would like to get some observing time. But with our university and several Belgian institutes, we are involved in a small part involved in the James Webb Space Telescope. So we contribute to one of the instruments, and in return, we can get a tiny fraction of guaranteed observing time. So we will get our hands on some data, but nearly every astronomer will be interested in getting some James Webb time.
I see there's one more question right behind, so yes, thank you.
Thank you for this presentation. So I was wondering if there is a reason, or the explanation of why there is a structured cosmic web rather than something that is uniformly random galaxies everywhere.
Yeah, that's not a trivial question, and that is what is called structure formation. And that is exactly what you see in this cosmic microwave background. So there, the cosmologists believe that the universe at very early days was extremely flat and extremely homogeneous, but some tiny, tiny fluctuations that could be quantum fluctuations froze out, amplified, and then you get very small overdensities and underdensities. So regions with just a little bit more material and a little bit less. And then gravity does its work. So the parts where there's a little bit more mass attract even more mass. And so the cosmic web gradually grows because of gravity, essentially. But it's a very complex program, very nonlinear. And so the way we study that is using supercomputers. So we try to simulate that, and astronomers we tend to reproduce what is observed in a fairly good detail there. It does match, of course. With a computer, you can tune the parameter until it matches, but it's not that easy.
Great, thank you very much. I see that meanwhile, we also have a few questions online. So I pass the word to Véronique.
Yes, Jonas is asking a question. Thank you, Jonas, first for being so active. The question of Jonas is the following. Given that the universe keeps expanding and stuff moves away from us in increasing rates, does that mean our observable universe is getting smaller as time goes on?
That's a difficult one. It's very hard to explain these cosmological things because you work in 4 dimensions and things do not move in straight lines. So you typically have to work with analogies, but every analogy breaks down. And I'm not very good at that. But ultimately, I cannot say, but at this moment, the observable universe increases because it gets older. So we can only look back 13.7 billion years ago, that's converted into distance, which is not 30.7 billion light years, because again, it's a nonlinear thing. But as time moves on, we will be able to see further into the past, and that means our observable universe will grow. How that will eventually be if things becomes exponentially expanding, I'm afraid I cannot answer that.
I think Hélène is asking about the same question. Do you have an idea of how big is the universe right now? I mean, in terms of dimension, diameter.
Not only I don't know, nobody knows, essentially. So we don't know, and it's very hard to know how big it is. We can only see the observable universe, but we cannot see what's beyond there. And whether it's finite or infinite, I think nobody knows. I'm sorry.
Okay, I have a question from Chris. Every cosmologist should have that question, he says. What is your opinion about dark matter, dark energy compared to other theories like the Mont theory?
Well, it's very annoying. So maybe to explain a little bit,
yes.
dark matter is some mysterious kind of material that we think is present in the universe and actually dominates the mass of the universe, because we needed to explain some of the observed relations that we see. Without dark matter, for example, it is very hard to see how galaxies can form. It is very hard to see how stars move in our own Milky Way. So that requires either an unseen form of matter that we cannot detect, so we call it dark matter, or it demands a change of the law of gravity, for example. Because you can also say, well, if it's not behaving in the way that it should be, it could be either that there's some matter that you don't see, or it could be that you're just using the wrong mathematics. And these schools have always been there and been competing, and they probably will remain competing. I personally believe there's a lot of things to say for dark matter, otherwise, because this the structure of the cosmic web is very hard to explain in a different way. On the other hand, it's very annoying that we don't know what it is and that everything we think it can be has been excluded. So it's a very big enigma, and so if anyone has an idea what dark matter is and can prove what it is, you can get your Nobel Prize, I guess. But I tend to believe that dark matter exists, but what it is, I don't know. About dark energy, that is yet something else, that is, again, something we have to come up with to explain the acceleration of the expansion of the universe, but what that could be, nobody knows. And there was at some point an idea, could be like the energy density of the vacuum or so, but if you then calculate what that is, it was a factor 10 to the power 100 wrong. So that was not really that good.
Mm-hmm. Okay, Katrien, do I have some time? Because I have some other questions.
Yeah, I think we can have one or two more. Thank you.
Okay, Karima is asking, have you encountered resistance somewhere in space or bizarre phenomena contradicting existing physical theories?
Yes, for example, the fact that we need to invoke dark energy and dark matter is just because what we thought were the laws that exist don't match the observations. So yes, indeed, we continuously have to change our thoughts on that. And for example, one of the things is, what is the role of turbulence or magnetic fields or so? These are things we have hardly ideas on. And once we think we understand it, we have new observations that say, well, this cannot be right. So yes, indeed, there's a lot of things that we have to reinvent every time we have new observations, absolutely.
All right. Luca is asking a question. Thank you for your talk, he says. How do you estimate the dark matter in your model? Do you use some observations, for example, using gravitational lens with Hubble or soon with Euclid?
Yes, so if we include dark matter in, for example, our simulations, we tend to use different sources of observations, for example, rotation curves of galaxies or gravitational lenses. And based on different observational evidence, some general theories have come up and we try to use those. But it's not completely out of thin air that we make something up, but we try to match it with observed data and we try to use different kinds of observations going from our own Milky Way to the universe at large scales.
Should we keep the other questions for later, or can I have one more, Katrien?
Take one more and then we'll move the rest for later. Yeah, I think we're quite okay on time actually, so we can do one more.
Okay.
Thank you.
Mike is asking a question from Switzerland. My question is, since we are facing challenging factors to see properly and study the changes in universe, how prepared are we for this adventure? It's a very philosophical question.
Well, I would actually contradict that. And looking at the graph that I showed before, on cosmological scales, we are not in a very in a very time-changing moment. Actually, the universe at this moment is very boring compared to 10 billion years ago. So we have things under control at large scales, and I think at short scales we have more problems.
Okay, thank you very much for this interesting Q&A session. And yeah, we actually have more questions, so I suggest that we keep those for after the talks. Yes. Same also for the public here, so you might have more questions linked to this topic. But let's move on, and thank you for the time travel, by the way. We will now return back to our own solar system, and we will go to the sun. And particularly the sun and its effect on its environment, our solar system. So we have Professor Giovanni Lapenta from KULeuven here with us, and he will talk about the sun in a microchip, understanding the sun and its impact on Earth using computer modeling. So Giovanni is a professor of space weather at KULeuven, an expert in space science, plasmas, high-performance computing, artificial intelligence, and nuclear engineering. He's also an expert in space science. Okay, I'm reading the same. While these areas actually might look very broad and separated, instead his research has brought them together in a number of applications. And lately, he's mostly focusing on space science and engineering and on fusion energy. Giovanni is the author of more than 250 peer-reviewed papers and recipient of the RD100 prize. Giovanni, we are very happy to have you here with us today. And I give you the floor. Thank you.
Thank you. Do you hear me?
Yes, we can.
And do you also see my screen?
Right.
All right, perfect. Glad it works. All right, so it's a real pleasure to participate, although remotely. This talk will be about the sun and its implication for us. So much closer to home, I would say. What you see here is the fact that I wanted always to start with the obvious statement that the sun is very important to our life and to our culture. So it has always been a central topic of investigation, let's say from religion to science. The sun is a ball of plasma. So first, what is a plasma? Okay, plasma, you can think of a plasma as a very hot state for matter. So when you take a piece of matter and you consider it in a solid state, you see that the atoms are more or less stationary. They may vibrate a little bit, but they stay in their position. As the energy is increased, if you give more energy to the system, the atoms start to remain connected with each other and feel forces that are attracted to each other, but they start to move around, and that's a fluid state, a liquid state. If you keep giving energy, these atoms finally break apart from each other. They get free from each other and become a gas. If you keep giving more energy, eventually the electrons and the nuclei of the atoms separate from each other, become free to move. So you have a gas of charged particles made of nuclei and electrons. The sun is in this state. So what is giving the energy to the sun to be in this state of a very high energy plasma? It's coming from the center of the sun in the core. There is a region of nuclear fusion. So that generates the energy. The energy that is generated in the core of the sun is irradiated out in form of radiation, photons, that propagate outward until they reach an outer layer, which is called a convective zone. In this convective zone, the plasma starts to form bubbles just like boiling water. And you have these bubbles that are coming up to the surface of the sun and bring out the energy that is released from the interior of the sun. So when this energy arrives finally to the surface, it brings out radiation, so light, but it also brings out currents and magnetic fields. So the sun is a big source of energy in terms of light, of course, we know that, but also in terms of electromagnetic energy is coming out of the sun. And this combined energy is the source of all the activities that we see in the what is called space weather, which is the topic of my presentation. So this energy coming out makes the sun very active. You see in this picture that is taken from the American Solar Dynamic Observatory, which is a spacecraft that takes images of the sun with unprecedented precision from space, presents areas of brightness called flares. So this is where energy is released at a higher rate. And there are sometimes these filaments of matter that come out of the sun, are ejected from the sun, are called coronal mass ejections. So these are two channels over which the energy of the sun comes out. But even under normal conditions, there is a constant flow of energy out of the sun, not just in the form of light, but also in the form of particles, which are called the solar wind. So what you see in this picture is the sun taken from another mission. This is a very successful European mission called SOHO. It's been more than 20 years in function and is still working. Some instruments don't work anymore, but most instruments are still working. This one that you see there is from 1997, but it is still working. You see there an entire month. I'm going to run it again. And you see there is this emission, the constant emission of solar wind, but sometimes over the period of a month, you see these eruptions coming out of the sun. When you see the eruption coming out as a circular ball, that means that it's coming to the field of view. So since the spacecraft is near the Earth, it's coming towards the Earth. So occasionally, these big emissions of energy come toward us. And space weather is a discipline that tries to study this, the evolution of the solar wind and all these disturbances, the eruptions and the flares, and the impact that they have on Earth and also on other planets. So this is a nice movie from NASA. It's an artist movie, of course. It's not a real description of the event. It shows these eruptions, and then it tracks them as they evolve around the solar system and eventually reach the Earth and perturb the Earth's magnetic field that shields us from them. They don't reach directly the Earth ground, but they modify the magnetic field around the Earth and finally release some energy that comes down to the Earth. There are two main threats that come from these big events in space. The first is in space itself, for example, for astronauts or for activities in space, for spacecrafts, and that is the radiation that is associated with this big emission of energy. The radiation hazard is a serious threat to astronauts. And then the second is the impact that eventually this has on the Earth itself, on the ground, in the atmosphere. In the atmosphere, there is this, the beautiful images of the northern light, the aurora. But there is a more serious damage that can happen to the power lines and other long conductors, metals, where the modifications in the Earth magnetic field can induce current that can damage them. So when you look at the impact of space weather, you see at least 6 of them. There is impact in space for the humans, but also for technology in space. You have scientific impact, which is, of course, very important from an academic and intellectual point of view. But practically, there are all these other impacts. I would say that the 2 most important impacts are those on the ground infrastructure. That can be really serious damage. And the second is the possible impact that all this activity of the sun has on the climate of the Earth. We will see now both of them. Starting with the first. Back in 1859, when solar physics was just starting, thanks to a scientist called Carrington, there was a major event that lasted several days, from August 28 to September 2, and he measured it. I mean, he observed it. He took images. Of course, he did it by hand. He took images by drawing what he was seeing in the telescope. And that's a drawing that he made in 1859 of the origin of this eruption on the sun. And then what you see there on the bottom is a picture of, or rather a reproduction of the perturbations that were made on the telegraph lines. In some places, the telegraph lines caught fire, some telegraph stations were damaged, and then it took some time to fix all this damage. But that was 1859. Right now, there is a lot more infrastructure that can be damaged. So the estimation is that if the current event were to happen now, it would be a terrible disaster, because it would damage the power lines and it would damage the communication lines. It would be, there are estimates saying that this could be something that would knock off the power for several months, because the damage would be extensive to many transformers and it would take several months to replace them. So there is a serious concern about this called geomagnetic storms. A recent panel from last year, unfortunately somewhat foreseeing bad things happening, had identified two main threats to the global economy. In this case, it's focusing on the United States, and it was asking the question, what possible natural processes can lead to a nationwide disruption? And there were two identified. One is the pandemic. The other one is space weather, because those are processes that happen throughout the planet, damage the whole planet. So normally when you have an earthquake or an hurricane, you can ask the firemen or the civil defense of one state to go help another state. But when there is a pandemic or when there is a space weather event, everybody's affected. So nobody can help anybody else. That was unfortunately the case for the pandemic. So we need to be prepared at least for the space weather, since we were not prepared for the pandemic. And there's one good reason for studying space weather. This activity that I just described is not constant. There are periods when the sun is more active and there are periods when the sun is less active. What you're seeing here on the left is a picture of the sun taken in visible light. This picture, actually, you can do it, never look at the sun with your own eyes, but you can project the sun on a screen and look at the sun. You can make a little hole on a piece of paper, and then the hole will project the image of the sun on a board, whiteboard, and then you can see the surface of the sun that way, indirectly. Now, this is done by professional in observatories, and you can see these dark spots on the sun. If you do it right now, there aren't any, because right now the sun is very quiet. But in more active times, in a year or two from now, you will see some of the sunspots. So when you call sunspots, this dark spot on the sun are called just sunspots without too much imagination. If you count them, and you do that day by day, week by week, month by month, year by year, you find the plot on the right. And it's interesting, actually, this repository of all the measurements of the sunspots is held in Brussels at the Royal Observatory. If you do that, and it has been done since the 1500s, you can see that there is this nice 11-year cycle. During this cycle, the activity goes from being very active to be less active. Why is that? So the sun, as I said at the beginning of my presentation, generates all this energy. Among these energies is the generation of a magnetic field. So when you look at the solar wind and its magnetic field, you see that there are, in quiet times, the magnetic field of the sun is nicely ordered, a little bit like the one of the Earth. There is a North Pole, there is a South Pole, and in between it changes sign. That happens during quiet times. During active times, instead, the magnetic field of the sun starts to change polarity, and it becomes very chaotic in between the polarities. And then after a few years, it settles on the other polarity. So if it was blue on top, so negative on top, positive on the bottom, after a few years, it goes to the other side. Then 11 years later, the cycle starts again. So every 11 years, the polarity changes. And when the polarity changes for a couple of years, the sun is very active. That's the origin of this activity. So the magnetic field that is included among all these energy channels, the energy produced by the sun transmits outward, is the main reason why we have this 11-year cycle. Of course, the question is, what is the impact then of this 11-year cycle? One of the first questions is, how much energy are we getting from the sun? So when the sun is more active, maybe we get more energy. And when the sun is less active, we get less energy. This is indeed the case, but the change is very minor. This is a very difficult measure to do, and it has been done carefully both in Europe and in the United States. Here I'm showing the data of an old European project that I was the coordinator for about 10 years ago, called Soteria, and the work was done by a partner in Switzerland, the group of PMOD in Davos, and they very carefully took all the raw data from different instruments on different spacecrafts, which you see on top of the left picture. And you can see the raw data is rather different from mission to mission because there are calibration issues. But when you bring them all together under careful analysis, you find that there is a little bit of change during the solar cycle in the total energy coming from the sun, but this change is less than 0.1%. So has that an impact on the climate? Probably not. It's such a small number. However, when you look more carefully, you see that this change tends to be much larger at the high frequency of the waves. So for example, UV light has a much larger change over the solar cycle. The other thing that you find about the solar cycle is that it has a very strong impact on cosmic rays. So first of all, what are cosmic rays? Cosmic rays are radiation, high energy particles that are generated all around the universe, in our galaxy and in other galaxies by energetic events happening, for example, supernova explosions, extragalactic jets, and stuff like that. So they generate this, there is a constant, say, a radiation moving around the universe, and in our solar system is arriving from outside. And the sun interacts with this. It, to some degree, shields us from these arriving cosmic rays. But during quiet time, it shields us less because it's less active. During active times, the sun shields us more. So during the solar cycle, you have also an oscillation in the cosmic rays. You have more cosmic rays when the sun is less active. So what you see in this picture here is a measurement of the cosmic ray fluxes, measured from the neutron fluxes measured on the ground in 4 different stations around the world. And on top, you see the fluctuations of the sunspots. As you can see, when the sunspots are at their maximum on top, the cosmic ray counts is on the minimum on the bottom. So this counter oscillation between the two means that the cosmic rays are out of phase by 90 degrees, but are responding to the solar cycle. So the solar cycle then has an impact on the total amount of energy, on the energy on some specific channels, and also on the cosmic rays. So why is it important to consider the cosmic rays? Cosmic rays are important because they determine how much clouds we are going to get. So when you look at the cloud coverage at low altitude, so the clouds that we see, and you correlate the amount of clouds that you have with the amount of cosmic rays that are arriving, you see there is a clear correlation. And for that is that the cosmic rays form the nuclei that make the droplet of water form. And then you get the clouds from the droplet of water. So if there are more cosmic rays, you get more cloud formation. And the clouds then have, of course, an impact on the climate. So this is a channel that is studied a lot in how this solar activity can impact indirectly the Earth through the cosmic rays. So when you look at the longer term and you start thinking about climate changes, the data started to be taken seriously only in the 1700s. There are data from before that are obtained by looking at tree rings and other ice cores, places where you can try to measure the cosmic rays indirectly as they were back then. And then there's, of course, also some information about sunspots coming from, for example, Chinese astronomers, some impartial records from the long past. So if you look at that, you find that there is a very interesting feature, the so-called Maunder minimum, that is very much discussed in our field. So in the period that goes from the 1500s, 1600s up to the middle of the 1700s, the sun was very inactive. The 11-year cycle essentially stopped. There was always no activity. For 200 years, the sun was inactive. Not that this is, I mean, the motivation for why that is not clear. And also whether it repeats often. But also what you can see there is that the maxima of the peaks are also not always the same. There was a very active period from the 1750 to 1800, and then another one strong one from the 1950s to about year 2000. So the space age corresponded to a period of high solar activity. But in the last cycle, there was a big surprise. So I teach space weather every year to the students, and every year I show them the activity of the sun. And for a couple of years, we're always telling this, you know, it's very strange how we don't see any activity. for this year, you're an unlucky student because you're doing the class when the sun is very inactive. And indeed, the community was very surprised by this lack of activity that started around the year 2005, 2006, when the sun was supposed to restart activity, but it wasn't starting. So for a year or two, we were waiting and the sun wasn't starting the activity. And then eventually, finally, it did. But as you can see, the last peak was very weak, much weaker than all the peaks before. What will happen the next one? We don't know. But it may be that we are heading for a new Maunder minimum. Maybe not. Maybe the next cycle will be strong. The predictions are, there are some models to predict this. Predictions are that the next will also be weak. And maybe we are indeed entering a phase where the sun is less active. However, the last peak was not totally unusual. If you look at the one from, let's say, the 1820s, it was also similar. And then after that, the activity restarted. But what I'm saying here is that the activity over the 11-year cycle is far from always uniform. Yes, it's 11 years, but sometimes it stops, sometimes it's more active, sometimes it's less active. Now, this is all extremely important for a reason. During the Maunder minimum was a period in Europe known as the Little Ice Age. The farmers had a hard time growing their products because it was so cold and the plants didn't like the coldness. And that's a period where the Flemish painters were very active also. And there are these famous paintings from the Flemish painters that shows like Amsterdam completely covered in ice and very, very northern-like climate in Flanders and in the Netherlands. So is there a relationship between the two? We don't have a complete knowledge about that, but it's something to investigate. Here is a study about the other big questions about this. Is the sun partly at least responsible for the warming of the climate in the Earth in the last decades? Because, as I said, during the space age, the solar activity was particularly strong. So if you, especially if you are the CEO of a petroleum company, you may think, yeah, maybe the oil is not so much the cause of this, but it's the sun, because the sun was more active. Well, this picture, you will have to interpret it yourself. And of course, this is a matter of investigation further. But the increase in the temperature in the last couple of decades is so dramatic compared with the activity of the sun that it doesn't seem that there is a clear relationship between, yes, there is a little bit more activity from the sun, and perhaps it's responsible for a little bit of a trend of upward. But the last 20 years, the sun actually now has started to be very inactive. There's less energy, and if anything, is trying to cool the Earth, and yet the temperature is going up very much, especially if you look at the upper hemisphere. If you look at the longest time record for the temperatures in the central England, because the British Empire kept a very good measurement of the temperatures in London and the area around London, and you can see there the difference is much less severe. Only in the last few years you start to see a significant change in the temperature, and in the last few years the sun wasn't very active. So, but I can't think for you, and it's an ongoing research. So, but it's a very important research too. This I already showed. The next one. Okay, so to understand all this, what I do personally is of course, observations are very important. I'm all for space missions, and here is you see in the bottom picture there on the right, the fleet of spacecraft that are currently or planning to study the space weather around the sun and discern Earth connection. But I do simulations, so we try to replicate all that happens in big computers. The one you see there on the left is the famous computer in Barcelona that is set in an abandoned church. It's a fantastic location to visit when you can travel again. So there are then two types of simulations that you can do of the sun. One is physics-based, where you try to use your understanding of the fundamental physics behind the sun, behind its activity, how the space weather events develop, to replicate them and to predict how they evolve. This is, for example, the work that we do in one project at KULeuven called U4. It's a European project. We are one of the partners, actually. A colleague of mine, Stefan Putz, is the coordinator, but there are many other teams. And these are examples of the simulations that we do to model this evolution of these eruptions. Here on the right, you see an eruption coming towards the Earth. But now, of course, besides physics-based modeling, there is a lot of interest in artificial intelligence. So now we are also looking at modeling these activities with artificial intelligence. This is an example of a modeling of the Earth environment, so the impact that these big events have on the Earth through artificial intelligence can automatically detect what is happening in different regions. That's another important area of research right now. Physics-based and machine learning, artificial intelligence should come together to give us a better understanding of the sun and its impact on the Earth, hopefully. That's the plan. So thank you. That was all I had to say.
Thank you very much, Giovanni. Very, very interesting. So I saw that there are already a few questions online, but I wonder if you have any questions here in the room? It will come, as it generally does. Yeah, I have I just wanted to appreciate how you talked about climate change and how the possible influence of the sun. A question that I have is if we are heading into a next Maunder minimum, that would mean that the sun has less irradiance, which would actually mean lower temperature. So you might have gotten this question before. Would that counteract what we are living now?
Well, the information that we have so far is not completely conclusive, and the models that are the climate models don't take into account this effect. So it's certainly something that the research should investigate more. But from all the information that we have of the sensibility of the models, it seems that the solar drive, it's a very small minority of the drives that are around. So the increase in CO2, in principle, based on the models that we have, should have a much larger impact than the sun would have. So I don't think it's going to save us. Even if there is Maunder minimum, it may decrease the temperature a little, but it's not going to be able to counteract all the increase due to the CO2, unfortunately.
Thank you. It's an important message.
Yeah.
Any questions here, meanwhile? If not, then I suggest we switch over to Véronique first.
Yes, there are two questions related to climate change again. Fatma is asking, much of the discussion around climate change has focused on how much the Earth will warm over the coming century, but climate change is not limited just to temperature. How about precipitation? Both rain and snow changes will also have an impact. So do climate models can tell us about the future rainfall?
Indirectly, because even the weather model that we see on TV every night, those models don't include rain. It's maybe not a widely known fact, but the weather model predicts the temperature and local conditions, and there are subsequent local models that are run by every country to have a guess of whether it will rain or not, but the rain is not included in the weather model. In the cloud models, there is inclusion of the clouds as in these large climate models. They include also the presence of clouds, but they cannot predict whether the clouds will rain or not. So you can say there is a certain cloud cover, but then whether it rains or not, it's up to. Unfortunately, it's something that is very hard to predict. So that is not known from this model. But climate models are not so much my area. I'm more like looking at what is the solar drive that go into their models, and then I will collaborate with experts on climate models to give them the input that we can give them, and then they can do their modeling of the climate. I focus on what's happening outside the atmosphere.
And also Mike from Switzerland, he says, during the solar cycle, 11 years, can some part of the world, arid countries, gain any positive effect in this phenomena?
Positive effects I don't see. Certainly there are many countries that are not affected. So all the countries that are near the equator shouldn't worry about it. But the countries that are closer to the poles are the ones that are most affected, especially historically. We have seen that happening a lot in Canada because the North Pole is more towards Canada than towards Russia. And also in South Africa. There was a major problem in South Africa, some transformers damaged by a space weather event. But typically it's more like Canada and North America that have to worry more. Belgium probably less, I mean, unless there is a Carrington event. Carrington event was seen even from Rome. so I mean, the northern lights that were done by, were caused by the Carrington event affected, were visible from Rome. So even in Italy that will be, but unless it's like a storm of that size, Belgium would not be affected. But we should be prepared in case. I mean, it's more than 150 years. Carrington-like events are expected statistically every 100 years. So it's not like a very, very rare event. It's an event that should happen on average every 100 years. So it may happen anytime.
Mm-hmm. Thanks. And then we have Michael. He's asking, what causes the solar cycle and the sun's magnetic field to rotate?
Okay, so that is the motions of the sun. When you look at the sun, actually, it's a very interesting feature of the sun. No, the Earth rotates as a single solid body. No, the rotation frequency, I mean, the velocity of rotation of the Earth is the same everywhere on the Earth. Around its axis, the Earth rotates as a fixed object. The sun doesn't do that. The equator rotates at a faster speed than the poles. So there is a continuous mixing of the plasma inside the sun by the fact that it rotates at different speeds at different latitudes. This rotation, which is called differential rotation because it's different at different latitude, is the driver of this 11-year cycle. And so that is the root cause. There are very complicated models that try to model this 11-year cycle and have some success in doing so. But it is, let's say, an open area of research to fully understand all the dynamics of the 11-year cycle. But we know what is the fundamental reason. Fundamental reason is the differential rotation.
Okay, that's it from my side. Katrien?
Thank you. I just saw a question that was posted in the chat and not in the Q&A session.
Okay.
So I think the question was from Tierno Ousmane from Senegal. Is there a particularity of the abundance of sun in the African continent? I think it links to the question that was asked before, the fact that you have just more sunshine in some places. Are they more affected maybe by this solar cycle?
No, actually less. The countries that are closer to the equator will be less affected because the magnetic field of the Earth would shield them better. While towards the pole, the magnetic field of the Earth, goes inside the Earth, so the energy can come in at equatorial, closer to the equator. As the tropical regions have much less, they feel much less the perturbances coming from the sun. So African countries tend to be less affected, except for the southernmost part of South Africa, like South Africa and the bottom part of Africa that is closer to the pole, so it feels this effect. But the variation in the light emission is really tiny, so it won't affect the countries that are at the equator. It's really the magnetic activity that affects the Earth the most. And in Africa, there is less affected. But that doesn't mean that Africa is not studying space weather. There are space weather agencies in many African countries, not just in South Africa, because there is interest for the power line and so forth also in other African countries. So Africa is actually building up in this area.
Thank you. That's very interesting. Great to hear. Are there any questions meanwhile here? I don't see any. And I think online, have we covered everything, Véronique?
There was one question from Fatma on, so why clouds hold the key to better climate models, but it's more climate.
I didn't hear. What was the question?
Sorry, why clouds hold the key to better climate models?
I mean, clouds are one of the main reasons. I don't know if you, I don't know whether the speaker is coming from Belgium or not, but if you are in Belgium, you notice how when there is a clear day, like tonight will be clearer, the temperature now drops more. When it's cloudy, the temperature drops less. So there are days where the minimum maximum temperatures are about the same when it's very cloudy. That's because the clouds do themselves a greenhouse effect. They reflect the infrared light back towards the Earth. So water is a greenhouse gas. In some sense, even more effective than CO2. So when you have a lot of clouds, you keep the temperature more. On the other hand, clouds are white, so they reflect the light more, so the albedo of the incoming light is more reflected. So it's a combination of the two effects. It's a very complex model that you have to make, but the clouds are a major aspect of climate.
Yes, indeed. I have questions for the other
okay,
speakers.
Yeah, then I think that now we can thank Giovanni, and probably we might get other questions, but maybe we can now go to general questions. So applause for Giovanni. And actually for all the speakers in this very interesting session. And I suggest that now we open the floor for general questions for all of our speakers tonight. Okay, and we might have still some open questions.
Yes, online. I have one question from Chris, who that was not answered yet. It was, I think, a question for Michael. For smaller stars, smaller orbits, I assume that tidal locking is more relevant than the larger orbits. Is that also taken into account when computing habitable zones?
Yes, indeed, it's taken into account. So the models that are used for computing the edges of the habitable zone around these kind of stars assume that the planet is in tidal locking. And these are global circulation models that are used, 3D models that are used and well suited for this kind of weird, peculiar configuration that were first developed to study the climate on Earth, and that are now applied to these tidally locked planets.
Yeah. I have also a question from Rida. Can physics confirm that any planet in the universe is in a cyclical motion?
Well, if by cyclical you mean a closed motion, no, because some planets have been ejected from the system. So these free-floating planets do not have a closed orbit. So it's an hyperbolic orbit. So they're basically traveling in the interstellar void and not orbiting around a star.
Then I have a question that makes the link between Maerten and Michael. In fact, do you personally believe in alien life? And related to that, that was a question from Jonas. And related to that, is there a chance to find an exoplanets in other galaxies?
Okay, for alien life, as a scientist, I have no faith. So I just believe in the scientific method that give us a better understanding of the universe. But if I had to bet, I would say that it's very likely that life exists elsewhere in the universe because all the ingredients of life exist elsewhere in the universe: organic molecules, water, energy around the stars. And furthermore, we now know that there are billions of potentially habitable worlds in our only galaxy. And I don't think that the emergence of life, we still can't reproduce it in a lab, but it doesn't seem to imply some cosmic accident. So we still can't, of course, infer its probability, but it doesn't seem to be something that is out of reach for science. So yes, I think that there's a very good probability that life exists elsewhere in the universe. And the second question?
The second is there a chance to find another exoplanet, an exoplanet in the other galaxies?
Well, there is a method that can be used. It's called the microlensing method. It has been attempted for another galaxy, the Andromeda galaxy, the nearest galaxy. There's been no detection yet. And I've read a paper recently that talk about a possible transit detection using a very peculiar method with X-ray observations, but it's a very tentative detection and it will be impossible to be confirmed. So there have been some attempts, but it's extremely difficult, of course, because it's really hard to get to resolve the stars in the other galaxies. They are very, very faint. So I think there's still plenty of exoplanets to detect within our galaxy before moving to the others.
Yeah, I can just add that there is absolutely no reason to believe that stars in other galaxies would be any different than in our own Milky Way. So if most of the stars in our own Milky Way host planetary systems, we can be pretty sure that that will be the same in other galaxies as well.
I also point out a question for Vincianne from Salma. Why do the majority of meteorites fall in this place exactly? So you were speaking about several places.
I think I was talking about Antarctica.
Antarctica and the desert, I think.
Yeah, the point is there is statistically speaking, with meteorite all over the planet, and probably with less meteorite falling at the pole than equator. The particularity of Antarctica is really this concentration mechanism. So we have no more meteorite falling in Antarctica, but we concentrate them and we keep them intact as well. So it's an observation bias actually, but we have no more meteorite in Antarctica compared to the rest of the Earth falling there.
Katrien, I think we are over the time, no?
Yes, actually we are over the regular time, so I asked Dominique. We have to round off, right? Yes. Yeah. Actually, with the people locally here, we can still answer some questions, but I think for the online.
And I would like to thank the speakers, of course, because it was super interesting, I think, for everybody. And so thank you very much for you. We are in live, but also remotely. Thank you, Véronique. You are far, but in your heart. So thank you very much. Thank you to Sabri. He's all the time with us. Thank you for your
Thank you, everyone.
For our team leaders also. Thank you. Now it is the best time. We have a reception upstairs in a very, very nice place. It's la salle des glaces. So you have to see it. So thank you very much. And goodbye to the others who are very far.
Thank you and enjoy. I miss you there.
Thank you.